5/21, April 16th, 2023. We've been reading, here's been some reading from Mark Swanson's Path Integrals and Quantum Processes, and also from Feynman's lectures about path integral. And yesterday or last time there was some talk about the 4-vector, the bivector. So we've been looking at the classical case of the path integral and about how it kind of has some simplified things that works up with Green's theorem for the time-dependent Schrodinger equation that resulted a closed form in t prime minus t and x minus x naught with respect to the momentum operator, deriving the value of the action. And about the quadratic equations, and about how the quadratic, or according to the triangle rule inequality, is ubiquitous. It's very central and present in a lot of different applications. That this idea that there's a parallelogon, a quadrilateral with parallel sides, and that it's square, that its sides are orthogonal to each other, and that it's in accordance to, however, it's so transformed that as a parallelogon, it still must maintain the triangle inequality, which it does, until such time as it reaches the particular ratio where the triangle inequality is not necessarily true, given the bounds and the regions about that. Kind of like a square in 4 subsquares with one piece missing. That's still 3/4 of it, but it intersects the missing center of the triangle rule inequality. And that's designed in the other aspects of the quadrature, and basically in accordance with the univariate parameterization of the whole thing, such an equation or such a value, that it works out why the quadratic is such a thing and a big deal. And then it gets into how there can be treatments of means about the quadratic, especially in regards to where it's more circular or spherical. The geometry, what establishes the metric, what establishes the vanishing area off the branches of the complex integral, and the otherwise the quadrature and quadratic is a really usual big deal. And another thing it gets into in computational complexity is the cases for 2 and 3 are different, and so you might easily notice that any number can be represented in base 2, and all the same numbers can be represented in base 3. But at the same time, a given base to the place representation, b to the p, or the expressing the number of combinations possible in a given fixed alphabet of n many letters in the alphabet, like 0 and 1 or 0 and 1 and 2 for base 2 and base 3, there still results in some of the combinatoric forms that 0 or 2 is particularly minimizing, and 1 is trivial, and 0 is vacuous. That 2 is particularly minimal, and then that 3 and everything greater is different. And so that just gets into why there's some of the reasons that there's, for Ramsey theory, and these other things that go on in the world of Birkhoff and the lacunary, why there are these measure theoretic approaches that have to take care about the measure, and thus the metric, and thus everything associated with it in all these fields, and also the measure in other aspects that have with regards to the test function or test particles, and those being discrete for continuous, or anything about the digital and analog, or anything about the particle and wave. That these are all relevant things that end up helping to explain, to add intuition, to get to where we have more of a Feynman-like view of things, that is possible then to understand that there's not just a blind man's guess that arrived at these equations, but they're almost always for a more particular setting than that which they're essentially as generalized, indistinct, and incomplete. Where there's the trade-offs of the one thing for the other. For the differential geometry, the trade-offs of the submersions and linearizations for completeness, where there's the trade-offs of the small angle approximation, for example, as we read about in this path integral development, and that it's a linearization. Or that in numerical methods, when there's only really computing the first few terms, that it's implicitly missing the rest of the terms, and that the nonlinear contributions end up being these higher order terms, especially when at least the first place they're started, getting off above these first order terms, is in the second, third, and higher order terms as the nonlinear terms. And that is a big part of the body of harmonic analysis and the theory of potentials. But that even above the theory of potentials, that being incomplete, is some theory of some potentials, or theory of omega potentials, that adds up to be why there's a super wave that results that either from the origin and classically and linearly, that the first derivative of position with respect to time is velocity. From the other side, it's the last derivative before it's zero, or along those lines. This notion of the dialectic is being built up to help establish why simple interpretations and extensions of usual interpretations of the settings of the theories of physics are easily wrong without understanding the adiabatic and non-adiabatic, or why is there no molecular contribution to these atomic equations, or why are there no wave contributions to these particle equations, or what are we doing on either side of the singularity of the black hole for Kerr and Chryskales and such on the one side, if I'm not mistaken, and Schwarzschild and Chandrasekhar on the inside. How is it so that on one side it's inverse cube, but the other side it's linear? Why is it so that in a lot of these equations we end up having this extra 1/2? Probably not because it was originally jimmied in there with the particular neat reasons why, as we read about last time, and about the Lagrangian and about the usual moments. But that's why it is there, because when they added it up and computed, it always worked out that was there. And so it could really benefit from a reason as to why that is so. So continuing on 3.2, motion with a source. In this section, an evaluation will be given for the path integral describing the system of a one-dimensional point mass simultaneously moving in the potential, VQ, and undergoing an arbitrary external time-dependent force, JT. So the potential field is called V, and I would think it would be velocity, and the time-dependent force J, and I'll call it for joules or input. The Lagrangian of this system is given by Lagrangian of Q dot Q equals 1/2 mq dot squared minus VQ plus JTQ, a differential equation, the second order, in Q, according to Q dot and Q. The function JT serves as a source for the particle's acceleration, i.e. it's the input force, and as a result, JT is referred to as the source function. The source function allows a definition of the generating functional, and this will be discussed later. When we hear functional, I think in this sense it usually means as a limit of standard functions. Otherwise, they would just call it a function. But it would be worthwhile to go back and revisit the exact definition of functional, just to make sure that when somebody says functional, when somebody says distribution, when somebody says function, that it's a function of a particular kind that is usually out of the CMT functions, and if it's a distribution, it usually also implies that it has area 1 for the entire integral in R. And the functional is as much the same, except it doesn't have that condition, and it's as modeled by a limit of standard functions, thus that it's established behavior and properties of the function in terms of these standard functions, and where it may not be necessarily what's called a real function. It might be not a real function. It might have these iota-values is the most clear definition, or the domain or range. Or it might have these Dirichlet function as an example. 0 at rationals, 1 at irrationals, or vice versa. Or 0 at any set dense in the reals, but everywhere discontinuous, and 1 everywhere else, and another set dense in the reals, and everywhere discontinuous. The function will be discussed later. It will be expeditious to begin with a simpler case of VQ equals 0 and return to the case of a non-zero potential afterwards. This is this tendency and propensity is imagine that besides it, you might describe it as a shuffleboard puck, and what direction maybe the deck is tilting vis-a-vis how it's carried forward by the stick. I can't say that I've ever played shuffleboard on a boat, but it's a model of same. It will be expeditious to begin with a simpler case of VQ equals 0 and return the case of a non-zero potential afterwards. The method of evaluating the path integral will be an application of the discrete method to the form equivalent to 2.47, which would, I imagine, be one of these classical cases. And if I have to consult for, which is the final form of the transition element according to the bracket of QBTB given QATA. And the measure appearing at ranges over the entire phase space available to the particle as it propagates from QA to QB. And you hear that phase space is a little underdefined, although path integral measure is getting a little bit better defined in terms of it being a measure, and what is 1.0 in this in these paths. The method of evaluating the path integral will be an application of the discrete method to the form equivalent to ... The appropriate Lagrangian density is given by LP comma Q equals PQ dot minus P squared over 2M plus JTQ, which should be familiar as an inverse application solving for the momentum in terms of the force, and with respect to that reflecting a differential equation thusly in those terms. The measure 2.46 derived for this form in section 2.2 is appropriate since the particle's motion can range over all phase space. So when the author says it is appropriate, we can almost must read that he means must be appropriate, and is to be read in that 2.46 that he describes that measure is appropriate, and that is so, and so it will be reused like so. The transition element is given by the path integral z QATA QBTB. The transition amplitude equals the integral from QA to QB of the dq's up to n, 1 to n minus 1, or those that are the beginning of each of those. If there are n many, here that 1 to n minus 1 is n minus 1 many. Of dp naught over 2 pi Planck dot dpn minus 1 over 2 pi Planck, or those or the dp naughts over 2 pi Planck to the n, because the positions are range from 0 to n minus 1, while the momentums range from 1 to n minus 1. Thus that it kind of is building in the reasoning why the momentum exists only after each thing or whatever with regards to the initial value, that it so reflects that it adds up this way. Although I'm not quite sure why it would just be left out. It might just be read as 1 to otherwise be able to sum those terms together or write a product form for those terms, and that they would have the same indices of production, though it's writing that for these raw differentials that he just indicates as such by an ellipsis among them, and many, however many are in between, ... That quantity times the exponent of I over Planck sum from j equals 0 to n minus 1 of this quantity, p qj plus 1 minus qj, pj qj plus 1 minus qj, minus epsilon pj squared over 2m plus epsilon j tj qj, that it's in the term of the sum, as the power term grows for this complex Gaussian integrals to still be stood up, squared out, and maintained. that the rest of the equation looks quite more similar to the previous equation in the classical case of the free particle. Looking back and how that is different, because it basically indicates that there's the force and then also that there'll be the potential added on later. In that sense, he's kind of adding piece by piece the input force for the potential, whereas another approach might have that the other way around, for example, or that otherwise the choice of direction he's taking for this derivation isn't necessarily unique to arrive at the same thing. And there's that, by applying the derivations in various steps, as it builds more and more constraints and assumptions, that is dependent on this declaration order as well. That it's so composed, what results defined is only the product of the previous definitions and declarations. Declarations and definitions are an idea from the formal language of computer programs, that a declaration is the signature of a function as according to usually input and output and return types for a plain function, and the definition is the actual body of the source code, thus implementing such. And so however that may be composed via reference to other declarations and ... So thus, he continues, rather than integrating the pj variables to create a path integral that is Gaussian in the qj, it is simpler to perform the qj integrations first. The result is a product of n-1 Dirac deltas, reducing the path integral to, in terms of the position operators instead, that the momentum is left out as a product of the force because it's computed and carried in. Z QATA QBTB equals 1 over 2 pi Planck. The integral of the dp's 0 to n-1 now, because those are the ones that range from n many, times the quantity delta epsilon j t naught plus p naught minus p1 ... or the production of all the delta functions, including is up to, according to the indices of epsilon j t n-1 plus p n minus 2 p n minus 1. Thus that it accumulates the terms. It forms a method of finite differences. Then that is figured as like, well, as well, these are the same methods of infinitesimal differences, because we have these iota values, and that is the working milieu. You can call it a metrizing ultrafilter if you want. You can call it this production, and it's on these raw differentials, and then it's in terms of the Dirac delta function, because it's boxed and squared away this neatly, and as results we can always point to the triangle inequality, say it's square. So in eliminating the momentum terms, which make it pretty convenient later when momentum is a thing, and momentum is a thing, times e to the quantity I over Planck, quantity p n-1 qb minus p naught qa plus epsilon j t naught qa. So a term in about the endpoints, the qa and qb, in terms of the infinitesimal infinitude between them, the p0 to pn-1, that qa is to p naught and qb is to pn-1, plus the epsilon times the j of t naught qa, that carries in. It's assumed to be an impulse force then, I guess. Exponent negative quantity I epsilon, so back into the Gaussian integral over 2m Planck, sum from j equals 0 to n-1 p sub j squared. First n-1 integrations are now trivial to perform. The resulting form for the path integral becomes equivalent to the single integral z qata qbtb equals exponent I over Planck qa at sum j equals 0 to n-1 epsilon j t sub j. So summing over the t sub j's, and that is a quantity this integral times this integral, I imagine, because it's e to that, times the integral of over r, I suppose, or just the integral over the space of the actions, the phase space, is there's no notation, of dpn minus 1 over 2 pi Planck e to the quantity I over Planck, pn minus 1 qb q minus qa, or the difference between beginning and end. It is still a term in there, kind of is dependent on those as particulars, minus I over Planck, sum from j equals 0 to n minus 1 epsilon over 2m, in brackets pn minus 1 minus sum k equals j plus 1 to n minus 1 epsilon j to k quantity squared. So that's contributing the quadratic factor, or the factor in the second order, yet in infinitesimal is about the impulse force, or j, and j is a function of time, the force, as for each of the infinitely many and infinitude of path elements along the way, or iota-values, iota. When I say iota, I mean a term like epsilon. It's arbitrarily small, but it's also non-standard, and it's the arbitrarily smallest positive and strictly positive value greater than 0. And an infinitude of those, just like these path elements, adds up to 1. Then that their integral, it's also an integrable function to make them like so, also equals 1, is also non-standard. Because when splitting them out, it would look like 1/2. Because it would look like just like a triangle that was split into infinitely many pieces, and that each dot that was left would be a point between 0 and 1. And you figure the area under that would be 1/2, but it's 1. Also called the F sigma Lebesgue integral. Expression is actually simpler when the continuum limit is taken, denoting the integral over j sub t as the impulse I sub t. The continuum limit here is, as he's describing, is bringing this back together. That is simpler to do that, and then as I've just described about iota values, there are things to do with that are explaining why, for example, you could put in 1/2 there instead of later in a more contrived contrivance that adds other assumptions you don't necessarily want or need to get that for free, at the cost of having built it in as a formal device, which would only have the same contradictions as the existence of these path elements anyways. I mean, if you're going to point to any kind of formal rigor in this development, when you look at these path elements and say, hey, aren't those non-standard constant infinitesimals between 0 and 1, like standard looking infinitesimals? It's like, yep, exactly they are. They're no different. And so their existence as a model of what would be iota values must somehow exist. In quantum mechanics, denoting the integral over jt as the impulse it is on the order of the integral from t to tb of d tau j tau, so it equals the integral from ta to tb of d tau theta tau minus t jt, where earlier there was described what tau was. And I'll seek to refresh my memory briefly because it's been a few days. And I remember considering how tau and t were the same, and then to establish how they're different, that's about the Euclidean action and the Wick rotation, that was what was gotten into with regards to that being a contrivance of sorts that makes it so that there's a corrective term for the Gauss integral, and that's the actions are well defined in terms of that reciprocating and oscillating as about a negative time, because negative times don't exist. There's only positive times. But tau might be complex or negative, or in such a space. Thus reading, easily written as Gauss integral, and writing denoting the integral is, this is the impulse then, that the integral over jt is the impulse. So this is force applied over time at work, or what? Vis-a-vis force over distance. and writing p sub n minus 1 equals p in the limit, epsilon goes to 0, the continuum limit, or the limit, that epsilon goes to 0, and the path integral becomes z qa ta qbtb equals e to the I over Planck qa ta. So that's been reduced, is pulled out j as a function in terms of it being I, the integral, or the impulse, times the integral of on r of dp over 2 pi Planck e to the quantity I over Planck p qb minus qa minus I over Planck integral from ta to tb d in dt of this quantity p squared over 2m minus p over m quantity times it plus 1 over 2m I squared t. That many of these functions have the functions as what define them, it being in the on the order of those functions and also in the exponent, and as in so far as they occur also in the integral, is expressing where their boundaries are, and it's really helping to just rewrite these sorts of integrals and expressions, because that way it's just defining how these things, according to however they change, it's in these few simple lettered terms of these reasonably low ranks or orders. And this way that it makes it tractable after it's in a sense fungible, and not just tractable when it's computed or crunched, but tractable also as it's manipulated and developed. But then that gets into the complications and reasons why that these definitions, each piece, as they're kind of reusing the same concepts as before, but rewrite the symbols for themselves, or introduce new variables, or do substitutions, or any other manipulations, have that it would be relevant in a case for writing this in electronic form, or just writing this in an annotated form, that the annotations would basically indicate how you could replace these various sections, or exactly what sort of manipulation and transformation is applied. And I'm not so sure of what that would be in terms of formal mathematics, how it's declared specifically exactly under what conditions manipulations are applied to the formulas that make the derivations, because it's always usually in the usual sort of language of proof, such that the elements are so arrived at have clear terms that refer to previous terms, and that is just a matter of reference in large part, and also reference and application, and then what carries or what gets accumulated in the annotations, thus that any reference to any annotated formula or equation results that it's also the monadic or the pure function, that the closure of that, and also in programming language terms, in terms of its definition, would be the accumulation of all those conditions and such. Thus would hopefully result being that given a particular single numbered equation or formula in the reference treatise, it's possible to expand that and unfold it into what all its derivations might be. And then even it would be particularly good where, just like in the writing of definitions of attributes combined, or has a composition in the software programming, is for ideas about how to make it so that such software programs as the developments of these formulas, algebraic symbolic notations, that it's possible to help build out why these can be rewritten in a way that makes them so composable, and also in a form that when it's besides what is our usual working memory term, the formula, as it's being developed and as it's being explained how it's developed, that it can also be accompanied with a sort of a language of formal annotations, which would help build up how this is and how it's put together, and how it falls apart, and how you could reassemble it under other given conditions, or given what conditions are the same or different, shows you what's left of otherwise that in any invalidation of the validity of the entire development results a null. Performing this final integration gives 2. this final integration, after rewriting it as a Gaussian integral, which I'm to read here, that expression 3.20, which ended up being an integral in I squared over t, and as that being the complex contribution, or in I, and then that's made into this Gaussian integral, is easily rewritten as a Gaussian integral of the general form, 1.107, the Gaussian integral, is ZQA TA QB TB equals e to the I over Planck, this usual this complex part is about the Planck's issues with the Heisenberg picture and the Schrodinger picture, times this quantity q sub a I t sub a minus 1 over 2m integral from ta to tb of dt in dt of I squared t again. So what results was most of that expression that was the in the terms of the impulse function is brought out as a function. It's in the e to the I times the integral over r of in dp of 1 over 2 pi 1 over Planck e to the negative I over Planck p squared over 2m tb minus ta plus I over Planck p quantity qb minus qa plus quantity 1 over m integral from ta to tb dtit. So in this manner, it's rewritten as the Gaussian integral, and it's in terms of how, particularly how I is, and e to the I is a present thing, and that there's some deconstruction to be done about Euler's identity, or e to the I pi equals -1, and about how the infinite roots of unity are so relevant, and that the infinite roots of I become so relevant, and that the very particulars of this branch and the commonplace or happenstance existence of real values or sensible values in these forms are sort of assumed, but that after the algebraic manipulation, it's guaranteed in a sense, but it's really is to make that having reached something like this at a point and just using this as an equation would very well risk not knowing all the things that are underneath it yet, or at least there's that. Although so far I have a pretty firm understanding of why these things are and what else could be put in their place. That what else could be put in their place to replace them is basically a definition of what suffices as them a model of them for model theory. That given the particulars of the model here is that it might be more of a model of something else in some such cases, in which case it becomes that that is unambiguous what the result would be, or not. Performing this final integration, the Gaussian integral just read, ZQA TA QB TB, the transition amplitude, equals root quantity m over quantity 2 pi I Planck TB minus TA, that having been carried out from the integration of the previous expression, e to this quantity I over Planck quantity m over 2 qb minus qa squared over tb minus ta plus this quantity qb minus qa over tb minus ta, or for the ends, the differences between the ends and beginning of the amplitude of the momentum in time. Integral of from ta to tb, the bounds of integration, dt it, the impulse, plus 1 over 2m tb minus ta, or the divided by the length and time, and with respect to 1/2 and 1 over m, or inverse proportional to 1 over m, while this 1/2 term is in place. Integral from ta to tb at dtit quantity squared is squared in proportional to square in impulse, just like acceleration is when it's the integral of this, according to what the force is, because force equals mass times acceleration, but here it's impulse, or the force generating momentum over time. that the momentum is in v squared. Plus qa times I t sub a minus 1/2 1 over m integral from ta to tb dt I squared t. Another thing is when writing the coefficients, or otherwise after canceling according to algebra, getting the least terms and writing that as a numerator and a denominator, or above and below the divisor bar, that here these terms like 1/2 and 1 over m are there for different reasons. And when I and Planck are there for various reasons, it would almost make for a more concise or specific notation, replacing this constant everywhere with I over Planck, or replacing this constant everywhere with I times Planck, and helping to reflect when or where it's relevant that the inverses are as about the mass, which is the free parameter, as about the time, which is with respect to a given fixed t0 or t0, also called ta, and that t infinity is tb, and also with respect to something like 1 over 2 pi, and the difference between 1/2 here and 1 over 2 pi, or not, when they're as well combined, that there's something to be said for helping you keep in mind and identify for each of these parts of the formulas what ratios they really represent, vis-a-vis what can be written in a final closed form that anybody can plug into any calculator and can compute. Although the final expression, 3.22, appears quite complicated, it was relatively easy to obtain by the path integral technique. It is a simplifying step to consider expression 3.22 for the case of a constant force, Jt equals F. The integrations appearing in 3.19 and 3.22, that final one and the initial one that established the impulse, can be readily evaluated for this case, and it reduces to z qata qbtb equals the root of m, or proportional to m, root m, 1/2 pi I, or 1 over 2 pi I Planck quantity tb minus ta, or inverse proportional to time and then proportional to mass and taking the root, so it's proportional to the root of the mass because everything else is unbounded or a constant. Time and as regards to that, it's in terms of mass and time, mass per time, or the root of that in the units, times the quantity e to the I over Planck quantity m qb minus qa quantity squared over times 1/2 times 1 over tb minus ta plus 1/2 qb plus qa tb minus ta f minus tb minus ta cubed f squared over 24m. With regards to 6 factorial, or 1/2 times 1 over 4 factorial. With regards to that being carried out as after constants of y, when it's a constant, it results that it can be so integrated. And it's on the order of f squared in the exponent. And then the exercises read, show that the argument of the exponential appearing in this previous one is I over Planck times the value of the action evaluated along its classical trajectory for the case Jt equals F. So, where the action was the 3.15, and that was just read as the Lagrangian, and which is p q dot minus p squared over 2m plus jt over q. The f is in terms of I, and then that I is the integral at j, is that it would so result for that Lagrangian there that it would involve putting in those different places where it just, that's why it helps to explain why what j of t is basically a constant. And then it results in a simpler form because there's because it's a first order ordinary differential equation in Q, that with respect to that and at the times, then that can be a function of time. And then with regards to that being I over Planck, is that I over Planck must have been canceled out as from the final integration from the Gauss integration. So as from bringing it up and carrying it back down, that's the term that gets left in, is this I over Planck's h bar. It's a very, very, very small constant in terms of the size of the atom in its width or its mass. It's small. That would be the argument of the exponential appearing in 3.23. So that would help explain then that if it would be the value of that in the exponent, then that would so carry down also. And that this exercise is helping me understand how to make the derivation, assuming that the exercise, of course, arrives at a particular derivation that would fill a few more paragraphs and roll back to how I think given thing is. Once its outer product was taken by developing in terms of the integral of the integral of the force input, and then when that's constant again, then it kind of falls back down to what results this thing. And exercise 3.3 reads, use 3.23 again to show that the transition element between two instantaneous momentum eigenstates, bra of PB/TB given PA/TA, is non-zero only if the classical impulse relation PB equals PA plus FTB minus TA is set. What that is saying is that the transition element between two instantaneous momentum eigenstates is non-zero if PB, the end position, is an exact function in time according to this constant function of force, that otherwise the transition element would fall out somehow. Whereas the previous case would kind of establish that it is met, but if it's not, then that would imply something else was let out of it, I think. I'm not quite sure exactly how to how to describe that yet, except that it's a very particular contrivance, that it's only in terms of these iota values being held up by their frame of the numerator and denominator, and those being all the elements, and those always having the same width, which goes to 0, adds up to 1, that's the thing. Otherwise, it would have that those transition elements would be not having measurable analytical character, that these are measurable sets. Although there's not a standard measure for it, there's like the Jordan measure, or what's in place, in effect, in this physics. Because mathematics sort of has an issue with it. Formally, for foundations. And then going forward, there it says, inspection 3.22 shows that it reduces result 3.4 for the case that JT equals 0. By definition, Z, QA, TA, QB, TB is given by 3.22 is a functional of JT. So for convenience, it will be noted ZAB, J. Z sub AB, bracket, J. So a functional, so it's for the operator, it's a functional, it's defining a function in terms of functions, and here it's just declaring that this function, the transition amplitude between A and B, is given as a function of this function J, which is J given M, given a QA, TA, QB, TB, and that it's derived as a function, so that it must admit that this it has bounds, just like or regions that are defined by bounds, just like an integral derivative. This functional has the important property that its functional derivatives give the matrix elements and products of the Heisenberg picture operator QT between the two instantaneous eigenstates. Well, that's something to absorb. And I'm not quite sure if I've really got to the point of this section yet, which is to be continued motion with a source. Because we haven't got into the potential yet. And what we've established so far is a bit about the case about how this is similar to the classical, and that it's so built in terms of the solution for the linear in the classical, and that it's framed up in these terms, and the functional is provided, and it's about the Heisenberg side of it, or the linear side, with the position momentum being known or what, before it actually enters the collapse of the wave function and this sort of thing. The singularity of the collapse of the wave function. That, the next exercise 3.4 asks, show that negative IH of delta of this functional, or delta of JT equals the integral from QA to QB of dP dQ, and that's provided as by the classical that was just observed, called 1.07. If you'll excuse me briefly. After the Wick rotation, so these are the terms after the Wick's rotation convention: dP dQ, script dd, script dB, script dq, qt of exponent brackets I over Planck integral t to tb dt Lagrange p comma q, which is given as above when it's not the Lagrangian in terms of q dot q, it's the one in terms of p comma q. It will be an application of the discrete method, equals bracket qbtb given qt qata j, where the subscript j serves as a reminder that the propagator is to be calculated for non-vanishing source. That's where it's so that if the source is 0, then it wouldn't have the integral quite well defined or something like that. Or it's the case that the Dirac delta would not be well defined or something like that. That, it appears, is going to be written from the above by the definition of ZAB, and then that QT falls out in the middle because and the one over the negative I Planck, or I cubed, Planck, and then 1 over the J delta JT, that value for each of the this is a functional that in this manner it's only represented in the bounds of integration 0 to 0 for the Dirac delta. The QT, big QT, would be the Lagrangian, the Hamiltonian of the momentum, which when the Dirac delta is 0 would fall out, and otherwise would be the Hamiltonian, or I shall so determine from recollection, assisted by flipping back through the pages, such thing. And the Q operator, time-dependent Hamiltonian C-number functions may appear in the Lagrangian density. The final form of the transition elements is given by QBTB given QATA, so that's the outside parts of our bracket, equals that integral in the final form of the transition element, and that the IH falls out in front because it's inside, and so when that would take the derivative of that, so with that's just taking the derivative of that with respect to time. All right, I think that's, but I haven't really verified. I haven't completed that yet, but it's so. From exercise 3.4, it should be apparent that the expectation values of QT for the free sourceless theory. The free theory is the sourceless theory. Although there's some discussion that the free theory was the theory absent potential. But here it's just the potential is 0, because otherwise it is non-zero. For the free sourceless theory discussed in the previous section can be obtained by simply evaluating the functional derivatives at jt equals 0. Using the result that delta I of t prime over delta j of t equals theta t minus t prime, and the functional chain rule. There's a chain rule for functions I need to understand. The expectation value of qt is given by bracket of qatb, given qt, given qata, subscript j equals 0 equals negative IH and these functionals delta z AB of j, or the functionals, djt at j equals 0 path equals quantity qa plus quantity qb minus qa over tb minus ta times quantity t minus ta, all that times the functional zab dot at 0, like so. Because j is 0, and thus that it results that it's just results the same bracket, and then therefore he continues the nth order functional derivative yields the time ordered product of n factors of qt. With regards to the c numbers, and that it's differentiable to nth orders, and it yields the time ordered product of n factors of qt. Well, I should review that quite some more and make a chart and a summary that goes along of the variables basically they're introduced, and also a description of each of the kinds of transformation rules and the manipulations that result, each of these developments in the formulas that so result that there's been computed sort of the outer product given these variables, first adding into this system of equations. Here's a placeholder for the velocity term, and here's a placeholder for this potential term, or rather vice versa. V is for potential, and the J term is for the force applied. So these are the sorts of things that would go into making for a summary, a synopsis, to carry along with the curriculum, to then have that for recall and reflection, basically the note card or what, that makes the systems of the series of equations and their derivations result, so that it's not so much memorizing an equation as looking up the pieces that pull it together and then comprising those together. Well, that said, it's about what I can read from that for the moment. And it's getting a bit, there's not so much to be said about the intuitive side of that right there, except it's building up and over some of the conditions that were already made. So that was a pretty formal exercise. That was a pretty linear section in the book, because most of it did not involve trying to train our intuition or arrive at the reasons why that certain particular methods hold up certain other conditions and this kind of thing. Yet a bit so more just plain manipulations, and there's quite a bit left out, and that goes into then how it so arrives at then there's both this outer explicit form, and then there's also the integral forms in terms of defining things in terms of integrals, just because you can write anything as so parameterized by time by just putting enough integrals or derivatives of its time in front of it, or that otherwise it's a very general form. Then to get from that, according to then what these other things are held, here about, well, what about when the potential is 0, or what about when the force is a constant, or what about when the force is a constant and 0? That those are things result then setting back to then that then there's a way to look at it that it appears to square up, that the bracket that the bracket has in the middle, then this Hamiltonian of the momentum operator, and that otherwise it results that in line with some of the other formulas from the previous section. The momentum operator and the transition amplitudes here is key. That the transition amplitudes eventually arise as a result of the momentum operator, but momentum is in a sense virtual as a quantity, and it's vis-a-vis mass, which is a real quantity here, and dislocation in time. So that said is about what I read into that, and that there's not much more of the intuitive say of that today, except that was about it. That's my intuition of those things, is about how they deserve a naming of sorts, and then that each of the various questions going back to the formal decorations demand a sort of formal annotation. That then it would be so possible to kind of read along and say, I've read in this section here in the usual mathematics speak of things in English, and that then besides this math mode formula, then also there is an annotation that expresses what happens according to the declarations in the English mathematics of the English language of the mathematics variety, and the actual transformations with so result, and their composition. All right. Let's see what Feynman has to say then. Let's see, in this book of lectures, here's a volume 3. How about 8.5? Let's see, 17.3, 6.1, 8.5. What are the base states, oh, that's 8.3, of the world? How states change with time. And he talks about the scattering matrix. So the scattering matrix is key with regards to scattering theory and tunneling theory, and that quantum mechanics occurs according to scattering theory. And the S matrix. So the S matrix is basically the lattice in which all these waves live in terms of a medium of propagation, or the field occupation numbers, where the mathematics field is an algebra that has addition and multiplication, for example, or two defined operators. According to these operators have various properties about all the elements that are so closed and exist in this algebra. Whereas physics' field is a section of space-time, or all space-time, and quantum numbers for each point in it, and what are these field occupation numbers, they call them. And then scattering theory is how things propagate in this field. So these propagation equations we're discussing are micro level or atomic level indications of this. So then when we talk about scattering theory in the S matrix, that's kind of whatever isn't included from that. Besides what is included in that, it's just kind of like a volume with regards to atomic motion, that with regards to waves or like molecular motion, if it's any different than atomic motion in the same volume, it's similarly what is scattering theory. And then tunneling theory is the complement of that, when scattering theory is what scatters, and then that actually still occurs, that it does go in a line from point to point, tunneling. And in particular is that those are the outsides of the theory, vis-a-vis that the integral developments, like the path integral, is the atomic part of the inside. The inner products live there, and the outer products live in the matrix, this S matrix. On using the form 8.28, Feynman says this physicist would calculate the matrix bra ISJ, which is called the S matrix. So if you see a theoretical physicist pacing the floor and saying, all I have to do is calculate the S matrix, you'll know what he's worried about. How to analyze, how to specify the laws for the S matrix is an interesting question. In relativistic quantum mechanics for high energies, it is done one way, but in non-relativistic quantum mechanics, it can be done another way, which is very convenient. This other way can also be done in the relativistic case, but then it is not so convenient. It is to work out the U matrix for a small interval of time, in other words, for T2 and T1 close together. If we can find a sequence of such U's for successive intervals of time, we can watch how things go as a function of time. You can appreciate immediately that this way is not so good for relativity, because you don't have to specify how everything looks simultaneously everywhere. But we won't worry about that. We're just going to worry about non-relativistic mechanics. Well, I would like to know how it works for relativistic mechanics. I say instead of length contraction plus time dilation, it's length contraction plus time dilation added up and made space contraction. So besides, there's Lorentz. The Lorentz equations has a solution by a guy named Fitzgerald, and so anything that solves the Lorentz equations is sort of a model for relativity, and the idea is that objects passing through space actually everything warps space, and so it kind of it's kind of like one of those segmented centipedes that kind of moves itself along forward and then pulls itself forward while not changing its shape. And that's kind of what the space looks like. In the same sense, it's like, for example, at the instant when you pass something, there's the momentaneous snapshot. The last thing you see is then, according to persistence of vision, the same thing. That these are the kinds of things that get into why space contraction is real in some interpretations of theory about general relativity or relativity theory, according to a guy 100 plus years ago named Fitzgerald, who wrote some solutions to the Lorentz equations and established Lorentz invariance, which is above Galilean invariance, which is about velocity and time and linear time in velocity, which then also in this conversation we've been having is about that there's the first order of position is velocity, and the last order of deceleration is velocity. That rest doesn't exist with respect to deceleration, and impulse doesn't exist with respect to velocity. But they do. Only at the extremis, only at the poles, only as projected as the opposite of what so completes them. So, then this for times close together, including when they go to zero. So this is also implement another up above path element formalism or infinitesimals, iota-values. That's what the S matrix has to be added up by. And also, while you're at it, the geodesy from general relativity has to be this way too, because it's always current, meaning it's always having been instantaneously evaluated in time, from any moment to any moment. If we can find a sequence, but we won't worry about that. Suppose we think of the matrix U for a delay from T1 until T3, which is greater than T2. In other words, let's take 3 successive times T1 less than T2 less than T3. Then we claim that the matrix goes between T2, T1, and T3 is the product in succession of what happens when you delay from T1 until T2 and then from T2 until T3. It's just like the situation we had 2 apparatuses B and A in series. We can then write following the notation, section 5.6, U of T3, T1 equals U of T3, T2 dot U of T2 minus T1. In other words, we can analyze any time interval if we can analyze a sequence of short time intervals in between. We just multiply together all pieces. That's the way that quantum mechanics is analyzed non-relativistically. One problem then is to understand the matrix U of T2, T1 for an infinitesimal time interval. For T2 equals T1 plus delta T. He writes delta T as we might write epsilon or iota-values or dt. We ask ourselves this: if we have a state phi now, what does the state look like in an infinitesimal time delta t later? Let's see how we can write that out. Call the state at that time t ket psi t. We show the time dependence of psi to be perfectly clear that we mean the condition at the time t. Now we ask the question, why does the condition after the small interval of time delta t later? The answer is ket psi t plus delta t equals u t plus delta t comma t, or the u t2 and the t1, ket psi t. Well, that's a sort of a linearization of sorts. He's just saying we'll just add the value at each time, and that we'll basically use the fundamental theorem of the differential, and that delta d takes the place of delta h, and then we'll follow the same sort of derivation out of that. This means the same as we meant by 8.25, namely that the amplitude to find chi at the time t plus delta t is Bragg chi given psi t plus delta t equals bra chi given u t plus delta t comma psi t. Since we're not yet too good at these abstract things, let's project our amplitudes into a definite representation. If we multiply both sides of equation 8.31 by bra I, we get bracket I given psi t plus delta t equals bracket I given u t plus delta t comma t given psi t. We can also reduce the ket psi t into base states and write bracket I given psi t plus delta t equals the sum of j bracket I given u t plus delta t comma t given j bracket j given psi t. We can understand equation 8.34 in the following way. If we let c sub I t equals bracket I given psi t stand for the amplitude to be in the base state I at the time t, then we can think of this amplitude just a number, remember, varying with time. Each c sub I becomes a function of t. And we also have some information on how the amplitudes c sub I vary with time. Each amplitude at t plus delta t is proportional to all of the other amplitudes at t multiplied by a set of coefficients. So saying it's proportional to all of the other amplitudes is really what is the effect and intent of that. Standard infinitesimals are an exact infinitude between 0 and 1, and all of these here proportional means that there must be some defined basis for proportionality for it to be applicable in these other measure theoretic senses. Whether that's a straight line split into points, there already exists a unit line segment. It's proportional to that. Whether there's these other numbers or functions of numbers here, he says, this is basically what he's indicating, that these are the mathematics of these sorts that demand notations and formalisms closer to the notation. And then the earlier section where he's describing about just finite differences and like, well, first of all, we're just going to say that they add. And then we're going to get into this as he calls it, the abstract, or the total, like when we talk about the point, the local, and the global, and the total, that these path integral processes are like the local and also the local of that particle as it moves. But then this abstract matrix is the local of all the particles in a region and the global of them also. And the total is the whole universe, and a point is a given point. Well, all right. Well, I hope this was enjoyable. And it was pretty slow today. Weather's nice. It's kind of cold and fresh. It was raining before. The east side of the state is pretty good, though. About 350 miles away this morning. And it's just kind of bright and sunny and clear and cool. And it was just bright and fresh coming over. 5-10 mile per hour breezes. Coming over the mountain passes. Pretty cold, breezy. Easy peasy, as it were, you know. In terms of the mechanics of passenger vehicles. Well, all right then. Hey, have a great day.